You're about to see the most crystal clear explanation of solving higher order differential equation in entire YouTube. If you are not able to understand any concept that I teach you in this video, I will personally tutor you that concept for free. That's my guarantee. Let's get into the video. Let us start by understanding some basic notations that we are going to use throughout this chapter. The first notation, which is the very common notation, is derivative of y. We know derivative of y with respect to x is dy by dx. This can also be written as d by dx of y, which means derivative of function y with respect to x. Now this d by dx in this chapter will be frequently represented as capital D. I will write that d by dx as capital D. So in other words, this dy by dx can be written as dy, okay, just dy, where d is nothing but d by dx. So d is an operator, d is a operator d by dx. Okay, that operator d by dx in this chapter is represented as d. Now we can extend this idea to higher order derivatives as well. So d2y by dx square, the second order derivative of y with respect to x, can be also represented as d2 by dx square of y, which can also be represented as d square y. So this d2 by dx square operator or d square by dx square operator is nothing but d square, capital D square y, and so on. If I have nth order derivative of y with respect to x, this can be represented as dn of y. Okay, we'll remember this notation throughout this chapter. Now let us get into the general form of the differential equation that we are going to solve in this chapter. In this chapter, as the name suggests, that we are going to solve linear differential equations of higher order. That means we'll have third order derivative, fourth order, even fifth order derivative. In other words, we might have nth order derivative in a differential equation that we need to solve. Okay, so the general form of such a differential equation is represented like you can see here. So dn y by dx to the power n plus p1 dn minus 1 y by dx to the power n minus 1 and so on. So we have all these higher order derivative terms, and on the right hand side I have x, which is the function of x. Remember, okay, x is a function of x, capital X is a function of x, let's say phi of x. Okay, so this is the general form of the differential equation that we are going to solve. Remember that this p1, this p2, all the way up to Pn, all these are constant values. Okay, they are not variable, they are constant values. Okay, that's the form that we are going to have anyway. If we factor out y from here, we'll have an equation in the operator of d, which is d to the power n plus p1 dn minus 1 plus p2 dn minus 2 and so on, plus all the way up to Pn, and we are factoring out y from all these values. And on the right hand side, we have x. Okay. Now this equation can also be written, since this is a function of d, this entire part is a function of d. So this equation can also be written as function of d times y, because this entire thing is function of d times y is equal to x. Okay, that's the general form of the higher order differential equation that we will solve, which is f dy is equal to x. Now there is something called as auxiliary equation in higher order differential equations. There is something called auxiliary equation, which is obtained by doing fd is equal to 0. So if you write that equation fd equal to 0, that equation is called as auxiliary equation. Okay, that is called auxiliary equation. Now let's see how do we solve such a differential equation. Okay, let's go into solving of such higher order differential equation. Now in order to solve these higher order differential equation, which is of the form f dy is equal to x, solution of such higher order differential equations is given by y is equal to cf plus py. So basically we have to calculate two values. One is cf and one is pi. Now what is cf? Cf is a complementary function. Okay, cf is complementary function. Let me write it down. It's a complementary function. And pi is a particular integral. Pi is particular integral. Now let's see how do we calculate CF and PI. Now there are different situations for which it varies how you calculate complementary function and particular integral, and that is what this whole chapter is all about. Okay, so we will start by discussing different cases of calculating complementary function. Okay, before going into all those cases of calculating complementary function, let me just give you a quick definition of particular integral. particular integral is given by 1 upon fd times x. Okay, why I'm telling you particular integral before complementary function? I'm telling you because I want to discuss this special case when x is 0. Okay, when this x is 0, our differential equation will become f dy is equal to 0. So basically on the right hand side you have 0. Okay, so that function of x is 0. So when that function of x is 0, that means this x is 0, this pi is going to become 0. Okay, so if this pi is going to become 0, the solution of such a differential equation is just going to be y is equal to complementary function. Okay, y is equal to complementary function. Because that capital X is 0, 0 times of this is just going to return particular integral is equal to 0, which is why the solution of that equation, differential equation, f dy is equal to 0, is y is equal to complementary function. Now let us go into the different cases of calculating complementary function. Let's see what is the first step to find the complementary function. The first step to find complementary function is to find the roots of auxiliary equation. If you remember, auxiliary equation is given by fd is equal to 0. So we solve this equation fd is equal to 0. In other words, we find the roots of that equation and find the value of d. Roots meaning finding the value of d by solving fd is equal to 0. Now, depending on the values of d that come out, these cases arise. Okay. So for example, let's say if we solve for d and the values of d that we get are unique rational values. Okay. They are rational numbers and unique numbers. So for example, let's say if the values of d that we get are a, b, and c. Let's say there are three values of d that we get and they are all unique and rational. If they are unique and rational values, the complementary function is given by c1 e to the power ax plus C2 e to the power bx plus C3 e to the power cx, where this a, b, and c are the roots, unique rational roots of that auxiliary equation. Now, why do I have three arbitrary constant and three of those terms? Because I found three roots. If there was fourth root d, I would just add another term c4 e to the power dx and so on. Okay. So this is the situation when there are unique rational values of d. Okay. Now let us see what would happen if the value of d would come out to be repeated rational values. Okay. What do we mean by repeated values? Let's say if I solve and I found that value of d is, let's say, a comma b. All right. If the values of d are a comma b, that means a is repeated two times. Okay. It is also important how many times it is repeating. Okay. If a is repeating two times, my complementary function would be c1 plus c2x into e to the power ax plus c3 e to the power bx. Since a is repeating two times, I write a linear equation. Okay. And since there are three roots, there are three arbitrary constants that are right. What would happen if, let's say, if I solve for d and it would have come out to be, it is very important, okay, to know this. Let's say if I get a comma a comma a comma b, if the value was repeating three times, I would write a quadratic equation. Okay. So if it is repeating two times, I write a linear equation. If it is repeating three times, I write quadratic. So basically you just write the equation of one power less. Okay. Since this is repeating three times, I write the equation of power two. Since this is repeating two times, I write the equation of power one. Okay. So in this case, the complementary function would be c1 plus c2x plus c3x square. You just write a quadratic equation, then write e to the power ax plus c3 e to the power bx. All right, I hope that is making sense. Since this is repeating three times over here, I write a quadratic equation and then I write e to the power ax, which is a is the repeated root, which is repeating three times. And then I write the unique root, which is e to the power bx. So these are the situations for rational values. Okay. Either it can be unique rational values or it can be repeated rational values. Okay. Just be careful when there are repeated values. Depending on how many times they are repeating, you have to reduce that power by one and write an equation. If it is repeating two times, you have to write a linear. If it is repeating three times, you have to write a quadratic. If it is repeating four times, you have to write a cubic equation and so on. Okay, I hope that makes sense. Let's get into an example to understand this concept better. Now we want to solve this differential equation, which is given over here. Let's first convert it into the notation form in the operator d. So what do I mean by this? I can write this also as d3y minus 6 d square y plus 11 dy, okay, minus 6y is equal to 0. Therefore, if you just take y common or factor out y, this will become d cube minus 6d square plus 11d minus 6 and times y is equal to 0. On the right hand side, since it is 0, we know that particular integral is going to be 0, and the solution of this differential equation is just going to be y is equal to CF, which is complementary function. Now let us see how do we find complementary function. In order to find complementary function, as we discussed, we need to solve auxiliary equation. Okay, auxiliary equation is nothing but FD is equal to 0. That's the auxiliary equation. Okay, remember this is auxiliary equation. Okay, we need to solve this equation in order to find the complementary function. Okay, so now FD, which is function of D, is right here. So we substitute that. So we have D cube minus 6D square plus 11d minus 6 is equal to 0. Now we need to solve this equation and find the value of d from here. Now since this is cubic equation, we'll have to do something called as synthetic division in order to find the values of d from here. Okay, so in order to do synthetic division, we need to find at least one value of d. If you try value of, let's say, d is equal to 1, let's see if d is equal to 1 satisfies this equation. If you put 1 here, so 1 minus 6 minus 5 plus 11. So minus 5 plus 11 is plus 6, and then plus 6 minus 6 is 0. So that means we know one root is for sure d is equal to 1. Okay, so we know d is equal to 1 is one root. And if we want to find another root, we do synthetic division by just something like this. So we just draw a horizontal line, a vertical line. We know that d is equal to 1, we found is one root. So we just write 1 here and just write the coefficients here. So 1, minus 6, 11, and minus 6. Okay. And then take this 1 below. Okay. Multiply this over here. So 1 times 1 is 1. Add these results. You get minus 5. Again, multiply. 1 times minus 5 is minus 5. Okay. Then 11 minus 5 is again 6. And again, multiply this. 6 times 1, you get 6. And 6 minus 6, here you get 0. So one root is d is equal to 1, and the other root, so if one root is d is equal to 1, we can say that d minus 1 is equal to 0 is one factor of this equation, of this cubic equation. And the other factor will be from here. Okay, it will be d square, so 1d square minus 5d plus 6 is equal to 0. So this is another factor. Okay. So you are basically splitting that cubic equation into two factors. D minus 1 is equal to 0 and d square minus 5d plus 6 is equal to 0. So therefore, so you can write this cubic equation as d minus 1 times d square minus 5d plus 6 is equal to 0. Okay. I hope that synthetic division makes sense. You would have done that in somewhere in your class 10th or class 11th. But if you have any questions, feel free to post it in the comments on synthetic division. So here you can just write this equation. You factor out 6, so you get 3 and 2. So you just can write d square minus 3d minus 2d plus 6. So you can just write that minus 5d as minus 3d minus 2d is equal to 0. I hope you know how to solve quadratic. So therefore, you have d minus 1 times, if you factor out d from here, so you have d minus 3 minus 2 factor out from here common. So you have d minus 3 again is equal to 0. So therefore, you have d minus 1. I hope you can see that one factor is d minus 3 from here and other factor is d minus 2 from here is equal to 0. So basically, I can say that therefore, either d minus 1 is 0, or if product of three numbers is 0, either the first number is 0 or the second number is 0 or the third number is 0. Okay. Or I should say d minus 2 is 0. Therefore, I get either d is equal to 1 or I get d is equal to 3 or I get d is equal to 2. So basically 1, 2, and 3 are the roots of that cubic equation. So we get the values of d. Since these are, now let's get back to our case. So if we get the values, unique rational values, so since these 1, 2, 3 are unique and they are rational values, the complementary function is just given by c1 e to the power ax, c2 e to the power bx, and c3 e to the power cx. So I can just write it like my complementary function is given by c1 e to the power 1x plus c2 e to the power 3x plus C3 e to the power 2x. The sequence doesn't matter here, okay? You can either write 1, 2, 3, 1, 3, 2, and so on. But this is your complementary function. Therefore, your solution in this case is nothing but just the complementary function, okay? If you remember from the top, we just have y is equal to CF, okay? Because our particular integral is 0, because our right-hand side is 0, the solution of this differential equation is just y is equal to CF. So therefore, we have here we have y is equal to CF is our solution. Therefore, y is equal to C1 e raised to x plus C2 e raised to 3x plus C3 e raised to 2x. This is the solution of the differential equation that we want to solve. I hope that makes sense. Let's move on to next example. In the next example, we have, let's write it in the notation form of operator d. So we can write this d3 by dx cube as d cube y plus we can write this d square by dx square as d square y is equal to 0. Okay, let's factor out y or take y common. So we have d cube plus d square y is equal to 0. Okay, so in order to find the complementary function now, we need to find the auxiliary equation. So auxiliary equation is nothing but fd is equal to 0. Auxiliary equation is fd is equal to 0. Therefore, auxiliary equation will become d cube plus d square is equal to 0. Now we need to find the values of d from here or the roots of this auxiliary equation. Therefore, in order to find the values of d, just take d square common or factor out d square. So you will be left with d plus 1 is equal to 0. Again, product of two numbers are 0. So therefore, you have either d square is equal to 0. So either first number is 0 or the second number is 0 or d plus 1 is equal to 0. Therefore, remember since d square is equal to 0, I get two values of d from here, which is 0 and 0. Okay. Because it is square, I get two values. Okay. Both are 0. Okay. So remember, okay, this is d and this is 0. I hope you are not confusing between d and 0. Uh, or you get d is equal to minus 1. So I get three values of d from here. I get either d is equal to 0, I get 0, 0, and minus 1. So my 0 is repeated two times. Okay, so my 0 is repeated two times. If 0 is repeated two times, remember, let's go back to our case. If your root are repeated two times, I write a linear equation. Okay, and then for the unique value, I write the C3 term. Okay, so now let us write the auxiliary equation, or sorry, the complementary function. So the complementary function for this case is C1 plus C2x, just write a linear equation, e to the power 0x, okay? E to the power, whatever is the root, you write e to the power 0x, plus C3 e to the power minus 1x, okay? So these 0 is the root and minus 1 is the root. Since 0 is repeated two times, I write a linear equation. And since this is unique, I just write it separately. I hope this is making sense. It's very simple. Okay. So therefore, from here, I can just write it as C1 plus C2x. Remember, e to the power 0 is 1. So I can just forget it because 1 times this is this, plus C3 e to the power minus x. Now I get my complementary function. If I get my complementary function, and if I notice that on the right side there is 0, my particular integral is going to be 0. So therefore, my solution is going to be just y is equal to complementary function. So therefore, y is equal to c1 plus c2x plus c3 into e raised to minus x is going to be my solution of that differential equation. I hope that makes sense. Now let us look at case number 3 and 4 where we have imaginary values for the d. Okay, so let's say if we solve that auxiliary equation and find the values of d, and let's say d come out to be imaginary values. In other words, let's say they come out to be complex numbers. If they are complex numbers, let's say they come out to be alpha plus I beta and alpha minus I beta. Okay, Remember that in case of complex numbers, if alpha plus I beta is the root of that auxiliary equation, alpha minus I beta is also the root of that auxiliary equation. That's the concept of complex roots, that they always occur in conjugate pairs. Okay. So let's say these two are the unique roots of that auxiliary equation, which are complex numbers. In that case, the complementary function is given by e to the power alpha x c1 cos beta x plus c2 sine beta x. Okay. Remember that alpha is the real part of that root and beta is the imaginary part of those complex roots. Okay. Remember that because there are two roots, there are two arbitrary constants. Number of values of the d, which is the number of roots, is always equal to number of arbitrary constants that you will have in the complementary function. All right. Now let's look at case number 4, where D has imaginary values, but they are repeated. So for example, let's take an example, best understood with the help of example. Let's say if alpha plus I beta and alpha minus I beta are the roots, but they are repeated, okay? They are repeated values. Remember that it cannot happen that only one value is repeating. In case of complex numbers, both the values have to repeat, okay? Because they always occur in conjugate pairs. So let's say these are the four values of D. So since there are four values of D, there will be four arbitrary constants in our complementary function. So our complementary function will be given by, since they are repeating twice, those values are repeating twice, I will write a linear function. Just like in case of real rational values, I'll write a linear function. So I'll start with the same e to the power alpha x. So I'll write e to the power alpha x. Instead of writing c1 cos beta x, I will write c1 plus c2x cos beta x plus C3 plus C4x into sine beta x. Okay, that's how the complementary function will look like. Instead of writing C2, I will write C3 plus C4x, a linear function. Instead of writing C1, I will write C1 plus C2x, a linear function. Instead of two times, if these would have repeated three times, I would have written a quadratic expression here. So C1 plus C2x plus C3x square and so on, quadratic expression here as well. These remains the same. These remain the same. Even this remains the same. So that's the logic. Depending on how many times they are repeating, you write a linear function or a quadratic function or a cubic function. Basically, the expression that you write has to be one power less than the number of times it's repeating. So if it's repeating two times, you are writing a linear function. Okay, and so on. I hope that makes sense. Let's start working on some examples. All right, we have this example here where we have d3y by dx cube. We can write this in terms of operator d. So we write d cube y plus y is equal to 0. Okay. We can factor out y or take y common. So we have d3 plus 1 y is equal to 0. We always convert it in terms of that operator d. Okay. After that, we write the auxiliary function. Okay. Notice that on the right hand side, it is 0. So our particular integral is going to be 0. Uh, so our solution is just going to be y is equal to cf, like we have been doing. Okay. Y is equal to complementary function. In order to find complementary function, let's write auxiliary equation. I'll just write AE for auxiliary equation. So the auxiliary equation is D3 plus 1 is equal to 0. Let us try to solve this equation. This is just like A cube plus B cube. We know A cube plus B cube is A plus B, A square minus AB plus B square. Okay, just a basic formula. I'll write it down here if you want. A cube plus B cube is A plus B, a square minus ab plus b square. Okay, if product of two numbers is 0, either one of them have to be 0. So either d plus 1 is 0 or d square minus d plus 1 is equal to 0. So that gives you one real value, real and rational value. And you have to solve a quadratic for this. So if you find the value of quadratic, this is just minus b. So minus b plus minus square root of b square minus 4ac divided by 2a. So that will give you 1 plus minus square root of 1 minus 4 is minus 3 divided by 2. I hope that makes sense. That's just a quadratic formula. And then you have minus 1 plus minus root 3i, because the square root of minus 1 is nothing but imaginary number. So you have root 3i divided by 2. So that gives you minus 1 by 2 plus or minus root 3 by 2 I. Okay. These are two values of d, and that's another value of d. Okay. So now our complementary function is given by, so complementary function, remember for this real and rational part, it is just like we have been doing for real and rational numbers. You just write c1 e to the power minus 1x. Okay, because of that minus 1, you just write c1 e to the power minus 1x. And for this complex number, whenever it is a complex number, our solution is e to the power alpha x. So if this is your alpha, this is your beta. So it is e to the power minus alpha x, or sorry, e to the power alpha x, where alpha is minus half, bracket c1 cos root 3 by 2x plus c2 sine root 3 by 2x. That's the solution where this is beta, okay? This root 3 by 2 is beta, and this is alpha. Minus half is alpha. I hope that makes sense, because that was the complex number solution, and this was the real and rational for d is equal to minus 1. All right, I hope that makes sense. Now let us look at last two cases of finding complementary function. Let us look at the situation where the value of d from auxiliary equation is unique, real, but irrational. Remember, irrational means the values are alpha plus root beta and alpha minus root beta. Just like complex number, remember, even the irrational roots occur in conjugate to each other. Okay, square root generally means irrational if it's not a perfect square. If it was a perfect square, it would have been a rational number, and we would handle it with either case 1 or case 2 that we have been doing. Okay, but if it is irrational, they would occur in conjugate pair like you see here. All right, the solution or the complementary function in this case is just like complex number. It is very similar to complex number, but just instead of cos and sine that we had in complex numbers, we'll write hyperbolic. Okay, so complementary function becomes e to the power alpha x c1 cos hyperbolic root beta x. Remember, it is root beta here because there is a square root, plus c2 sine hyperbolic root beta x. Okay, that's the complementary function in case of real but irrational roots. Okay, what if d is repeated? It is a very similar situation. Instead of c1, I just write c1 plus c2x. I write a linear function. If d is repeated and irrational, so if it is irrational still and repeated, the roots will be something like alpha plus root beta, alpha minus root beta, but these are repeated in that case. So alpha minus alpha plus root beta and alpha minus root beta. So if these are repeated twice, I will write a linear function. If these are repeated three times, again I will write a quadratic function. Same concept, same idea here too. Okay, so let's see. In this case, the complementary function will also start with e to the power alpha x. Instead of c1, let's write a linear function. So c1 plus c2x cos hyperbolic root beta x. Okay, plus again instead of c2, write a linear function. So we have used till c2, so we'll write c3 plus c4x into sine hyperbolic root beta x. Okay, I hope that makes sense. A very similar idea. Because they are repeated values, you just write a linear function here and here. Rest everything remains the same. All right, let's move on to some examples of real and irrational roots. All right, now let's solve this example. Our auxiliary, since right hand side is 0, particular integral is going to be 0. So our solution is just going to be y is equal to complementary function. So in order to find complementary function, let's first write the auxiliary equation, which in this case is d square minus 2d minus 4 is equal to 0. Okay, you can just solve it like a normal quadratic. So our d is going to be minus b, so minus minus 2 minus b plus minus square root of b square minus 2 square minus 4ac, so a is 1, c is minus 4. Okay, divide by 2a, uh, divide by 2 times 1, so that will become plus 2 plus minus square root of 4 plus this is going to become 16 divide by 2. You can also use calculator actually to find this in your exams. So you have 2 plus minus square root of 20 divide by 2, okay, is equal to 2 plus minus this root 20 can be written as this 20 is like 5 times 4 and 4 times 1, so this is like 2 root 5. Okay, divide by 2, so this will become 1 plus minus square root of 5. Okay, now that's the value of d that we are getting from here. Remember, since it is 1 plus minus square root of 5, this 1 is your alpha, root 5 is your beta. Remember, this is real, but it is irrational. Okay, if it is real and irrational, your complementary function is going to be, in this case, is e to the power alpha x. So e to the power, I'll just write e to the power 1x. Okay. There is no repeated value. So the answer is just going to be c1 cos hyperbolic root 5x plus c2 sine hyperbolic root 5x. Okay. So basically, you write your first root in the power of e to the power 1x, and then this root 5 goes along with cos hyperbolic and sine hyperbolic x. Okay, remember there is x here as well. That's your complementary function. And if you know your complementary function, your solution is nothing but y is equal to complementary function, which gives you y is equal to e to the power x c1 cos hyperbolic root 5x plus c2 sine hyperbolic root 5x. And that's your general solution of that differential equation. I hope that makes sense. The concept is very simple for complementary function. Thank you for watching till the end. Please do check out my next video when it comes. Please do subscribe to my channel for particular integral and one shot videos for your engineering semester too. Thank you so much for watching till then. Take care and bye bye.